Welcome back, everyone. Moving on to 10.4, inscribed angles and polygons. Still the same standard, G.C.2. I understand and can apply theorems about circles. Starting off, we're going to start with a couple definitions. First definition we're going to start with is an inscribed angle. So an inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of the circle. Okay, so let's take a look at the picture we were given. First of all, we have an inscribed angle. That angle is ABC. So the vertex B is actually on the side of the circle. And then if we go from like B to A, that would be a chord of the circle. If we go from B to C, that would be a chord of the circle. So we would call angle ABC an inscribed angle of the circle. And in a little bit we're actually going to define the word inscribed, which means drawn inside. So the angle has been drawn inside the circle. Okay, moving on. Intercepted arc is the arc that lies. So the arc that lies between the sides of the inscribed angle. Okay, so if we take a look at our intercepted arc over here, that's drawn in blue. So that would be our intercepted arc. If you remember in 10.2, we went over that the measure of an arc is the same as the measure of the central angle. Well, this time we're not dealing with a central angle from the center of the circle. We're dealing with an inscribed angle from the side of the circle. So we're going to figure out a relationship between the measure of that intercepted arc and the inscribed angle. Moving on, measure of an inscribed angle theorem. The measure of an inscribed angle is 1/2 the measure of its intercepted arc. So let's say I'm dealing with the arc AB, and I know the measure of that arc is 60 degrees. Well, if I had the central angle that went to the center of my circle, then I would know that that angle there at C is also 60 degrees. But this time we're not talking about the central angle, we're talking about the angle that goes the whole way over here to D, so ADB. Well, what this theorem is telling us is that that is actually half. So the measure of that would be 30 degrees. Moving on, inscribed angles of a circle theorem. If two inscribed angles of a circle intercept the same arc, then the angles are congruent. So what that means is, let's take a look at this angle right here. Okay, and his intercepted arc is AB. Well, let's pretend for a minute here that AB is still 60 degrees. Well, then we know, because we have an inscribed angle, that angle D over here is going to be 30 degrees. Well, let's take a look at our other angle over here that goes from A to C to B. Do you notice that the intercepted arc there is still AB? It's still that blue part, which is still the same thing. So if that blue part is 60 degrees, then for the green angle, angle ACB, well, that's still just going to be half. So then it turns out that the red angle and the green angle are congruent. They're both 30 degrees because they both intercept the same arc. Okay, inscribed polygons. So those were angles. We were just looking at an angle. Now we're going to put a polygon, which is, if we forget, any closed figure. Okay, typically we're going to be working with triangles or quadrilaterals. Those are the big ones we're going to hit. And we've got inscribed and we've got circumscribed. So inscribed means drawn inside. So if you take a look at your picture, we're looking at the blue one. It's an inscribed polygon because it is drawn inside the circle. Versus if we take a look at circumscribed, that means drawn around. Okay, so if you look at the circle is drawn around or drawn outside of the polygon, so it's a circumscribed circle. So if I use the word inscribed, you need to know I'm talking about the inside. If I use the word circumscribed, you need to know I'm talking about the outside. And then also keep in mind, it doesn't count if you just take a figure and go like this and say, oh, that's circumscribed, it's on the outside. No, it actually has to like touch the figure. So this guy has vertices on the circle, just like the circle is touching the vertices of the figure. So the black one that I drew is not inscribed or circumscribed because it's not actually like touching all of the vertices. Keep that in mind. Moving on. Inscribed right triangle theorem. If a right triangle is inscribed in a circle, meaning I'm going to take a right triangle, I'm going to draw it on the inside of the circle. So look at your picture. Right triangle, inside of the circle. Then the hypotenuse is a diameter of the circle. So if you take a look at the picture, you can kind of see that going on. Conversely, meaning other direction, if one side of an inscribed triangle is the diameter of the circle, then you know that the triangle is a right triangle, or that it has a right angle. So let's think about this for a minute and why this would be true. If you're taking a look at angle A, B, C. Okay? If you look at his intercepted arc, it's AC. Well, if you're looking at that, you should also be noticing that AC is in fact a diameter. It's cutting it in half, which means this has to be 180 degrees because it's half of the circle. You can also think about it right here. That's a straight angle. And keep in mind the central angle is equal to the arc. But over here, ABC, the one I have drawn in blue, is not a central angle. It's an inscribed angle, which we just learned means it's half. So if the arc is 180 degrees, then that means right over here is half of that, meaning it's 90 degrees. Okay, and then if that's 90 degrees, then what it's telling you is, well, then this is a diameter of your circle because it's cutting your circle in half. Inscribed quadrilateral theorem. Okay, quadrilateral, four-sided figure, versus we just did triangle, three-sided figure. A quadrilateral can be inscribed, meaning on the inside in a circle, if and only if the opposite angles are supplementary. Do we remember what supplementary means? If not, make yourself a little note. Add to 180 degrees. So, take a look at your picture. You've got a quadrilateral EFGD inscribed in the circle. So, opposite angles. You've got angle D, you've got angle F. We know that they're going to add up to 180 degrees. Likewise, you've got angle E, you've got angle G. We know that they're going to add to 180 degrees. Which means, and some of us already know this, in a quadrilateral, actually let's back up a minute. In a triangle, all the angles add up to what? So think about that. In a triangle, they all add up to 180. Well, in a quadrilateral, a four-sided figure, they don't add to 180. They add to 360. So if the blue angles add to 180, and the red angles add to 180, and then we take 180 plus 180, then we've got 360 degrees in our quadrilateral, which also means 360 degrees in our whole circle.